for sharing. All right, you're recording, sharing. Sweet. All right, so for PA2, if you read the assignment, first of all, you're required to submit your code and the animation. I didn't ask for PDF because this starts with getting points from user. And I don't want you to have like default points to draw. So no PDF for this one, so you don't have to publish. We will run all the codes. We will check a couple of scenarios to give you full credit. All right, I'm going to talk about that here. Please don't copy paste this part of the code because I'm recording the video. You know, this is just the how to define the parameter though. Like if you want to copy paste it, it's not a big deal. But so I defined the two other functions which I'm not showing you, right? So you know that so this problem I'm gonna run so you can see what's gonna happen. Hopefully internet is going to be okay fast enough. So I expect you to show the workspace, right? So you can even make that gray or something to be very clear. So the area between the two circles is going to be your workspace, right? And we had a class participation, the small circle inside and the parameter around are outside of your workspace, right? So your code should also have the ability to show what happens if the point gets there. We're gonna talk about that. So you start from here, you draw that, you saw the piece of code, so you can just use that if you want. It's not important. So I used 5 points. You can go for more than 5 points to have a nicer curve, more smooth. You probably could do more points, but let's just start with default of 5. So this is telling me click on 5 more points within the reachable space, right? You're telling the user, and the workable space is this donut, correct? So have that message so your user knows what to do. Now first I'm gonna check all the points inside. And you see that I'm drawing, so it says 2 more points. That's like optional, right? So you're just reminding especially if you have more than 5, you're kind of reminding your user how many points is left. So you're just helping. And then I'm gonna do that. So this is a curve that was fit. It just happened that some part of it is actually outside of the reachable workspace because the points are inside, but the curve that was fit, whatever piece of code was written here, just fit it outside because you can draw so many curves between 2 points, right? So you can adjust that in your code if you want it. Now it says now smooth curve, press any key, tracking the smooth curve. So you saw what happened that we're going to discuss about that. So it's following the curve, right? So you saw here, when the curve was on the outside, it tracked this outer edge of the workspace. So one way is like send error, hey, the curve is outside, but I picked the point inside, right? That's your algorithm that draws the curve outside. The goal is to follow the track between these points. So here, this arm can follow here and then go on the outer limit. So in your code, you have to always check the distance. If it's greater than L1 plus L2, you're gonna track L1 plus L2 until you're back again, right? Inside that circle. So then that is done. You're taking a video of showing from the beginning, from the run. So the video I expect show this, your code, right? And then hit run. And then also like it has to be recorded from the beginning. And I want to see what happens. So let's pick points that they're all, let's see if I can pick things that are inside and very nice. Nothing is outside. Okay, this one is all pretty nice to smooth the curve. And it's tracking, everything is inside. Good, right? So I'll let this finish. Once it's done, I'm gonna finish the video and that's your assignment. Cases that I will try is, so you see that here we keep running and then picking different points. So it's very easy to grade for us. So we're gonna download everything. Make sure that you rename the code to your last name. So if we download all of them, it's easy to see whose code was what. Or you like team, undergrad team 1. That's probably easy because it's a group work. Grad team 1, then we can find who was that. So I'm gonna pick one here. I went outside of virtual workspace, right? It didn't like it. So that's how the code is code. So this specific code, if you pick outside, is not going to show it, but it still is able to track. So what it does is it goes track in between. And then you see that in the small circle, it didn't go straight. It went and tracked the small circle. I think because I clicked outside of this box, because it's a good idea to give it a box so it does not actually go everywhere, right? So if I was careful and I put, for example, I clicked here, let's do that for the sake of it. Let's say here, 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 and why not? You see that there are outside and inside. So this is wants to smooth the curve. So you can use techniques to smooth your curve, and then tracks the parameter outside, goes inside. You see the break there. So 2 arms. And then when it reaches here, it's gonna just track the circle. And you see, this is like actually the singular point, right? Because it's folded, but singular point doesn't mean it does not reach. You have just limited reach. And it just happens that L1 and L2 are such way that it could reach that point, right? So, makes sense? Now, if you are a grad student, I want you to maybe use more points and try to have some like cool, I just can use find cool word for it. So I remember last year, one of my grad students used flower, draw flower. You had to follow flower. So I had to do something with the curve to make sure that every time the curve is on the outside of the 2 points. So my suggestion is write this code for default 5 points, right? Once you have that, once you secure that, if you want to go further and be more creative, that's a better word. Be more creative with drawing your curve, you can do that. I remember one person did kind of a star, but it was curved star. So you had to go from point A, B, C, D, E. It was not all, so the sequence of the point was important to follow. So those are extra things you can do, right? So I'm leaving it to you if you had time to do that, but the minimum is what I showed you. As expected from everyone. And so that's how grading will work too. Yeah. Do you have a question?
I would just say to reiterate the renaming your MATLAB code, because if it has like a parenthesis like 1 or 2, if you download the same thing on your computer, if you ever seen that, like it'll keep downloading a new copy, but put like a parenthesis, whatever number it is. If you submit that, then I can't just straight up open it. I have to rename it.
Yeah. So like graduate 1, graduate 2, graduate 3, undergraduate 1. So you can say on 1, whatever you use, just don't say 1 because there's going to be 2 team 1, right? So that's easy for him. He will grade graduates first, then he grades undergraduates, right? Which also reminds me that Brett mentioned the our undergraduates also did really good on coding. So expectation is high for PA2. So very proud of the undergraduate as well. I think they did a very good job on the code. So kudos to everyone. I know PA1 was difficult. That's the goal. Like I give you the shot. So after this is going to be easy. So PA2 should be easy. Year is year. All right. So another, I'm going to stop this because I'm going to share the lecture. Another thing is that, yes.
Are we
You're in the same group. You're stuck with your teammates. Now that brings me to my point. If your teammate slacks off, they're supposed to do something by Friday. They don't do it until Saturday night. Email me right away because you have seen the pattern, right, on PA1. If it has start happening in PA2, email me. Then I will deal with that. You can, if you're in a team, the idea is you're sharing the load. Everyone has a schedule. You have to work with each other, right? The other thing is you can sit together, talk for 15 minutes and brainstorm. How do we solve this problem? once you know what the problem is and how to solve it, what's your approach, the coding part of it should not take time, right? You'll say, hey, Adnan, you go figure out this line and how we fit curve through 5 points, right? Because you know part of it, your approach is to do that. The other part is, okay, how now we draw the 2-link robot that can track? Obviously, we need inverse kinematic here, right? Okay, Michael, you write the inverse kinematic part. But then, okay, these are very obvious, but how things are going to work. That part you need to talk to each other. And don't wait for last minute. Talk 15 minutes, figure those out, and then divide tasks. And then if your teammate didn't deliver on time, email me right away, and they have to deal with me. Don't make me make all the PA assignments individual and as the same level of difficulty. I'm also gauging the class for final project, right? So be a good teammate. If your teammate, for any reason, they might just have too much to do and they cannot, inform your teammate, and then you can email me. I'll figure something out that works for both of you or all 3 of you. All right. I hate the slackers. I can't emphasize how much I hate that. You can't imagine what happened to me in my undergrad. Yeah, I had to do everything for the boys because they're lazy. All right. All right. No offense, our guys are good here. It happened though. I was the only girl in the class. I was the only one taking notes. Huh? That's what my husband says. Yeah. But no. But I'm taking notes for everyone, so I took that responsibility out from everyone. All right. So today we are going to go over Lagrange Euler explicit form. So we are going to solve, hopefully if you have time, I talk too much, of the same problem we solved on Monday, but using this method. And you can decide which one is easier and use that method. And on Friday, we will touch base on Newton Euler and then review of the exam. So tomorrow I'll post an example for Jacobian. And then hopefully by Friday, I post a practice exam for the class. All right. So Lagrange equations, explicit form, we are going to use that Lagrange equation and equation of motion, but the way that we develop our different segment of it will be different. If you looked at my annotated lecture for last class, I kind of expanded on this. So because you know, L is K minus U, right? And your tau equation of motion, we said is d dt L partial differential of L with respect to Q dot minus partial differential of L with respect to Q, right? But in my example, I just went directly use this one. The reason is that if you put L here, so d dt K minus U with respect to Q dot minus K minus L minus U, sorry, with respect to Q, you know that U, your potential energy is never a function of Q dot, right? It's always a function of your Q, K dot L, right? So that Q dot never appears. So when it's not a function of that, so when you get the partial derivative, it becomes 0. So we're just not even going to include that. That's why you can write it as this form for our case, right? For rigid body systems, our potential energy is just going to be gravity. Now, if you had a spring in there, that was the spring coefficient was a sign of something, theta or something, then that would be a different scenario. So you have to look at your system. But for now, for our system, rigid body, we can follow this simpler format. So the derivative with respect to time of partial derivative of your kinetic energy with respect to Q dot minus partial derivative of your kinetic energy with respect to Q. So I package these two on one side. I'm calling them inertial force because kinetic energy and are representing the inertial force. Then the other side, I put G, which is the partial derivative of U with respect to Q, which is non-zero here. I package it on the right side as torques and potential energy, right? So one side, inertial force, this side, torque and potential energy, potential forces, let's say, just representing. The reason is that I'm going to develop an equation, a relationship for the left side that we're going to use for explicit method. So for now, we're going to forget about G, the gravity. The reason is it's easy. Like the partial derivative first order with respect to our joint variable. That's the easy part. So I'm going to use the other two that represent inertia. So when it represents inertia, it will have a play in finding the mass matrix, right? So I'm going to keep it on one side. Now I'm going to expand it. So before that, if you remember, we said we can represent potential energy for our multi-body system as 1/2 Q dot transpose MQ Q dot. MQ is our mass matrix, right? Q dot is the velocity of our joint variables. That's a quadratic form. It's the same as 1/2 mv squared. It's the same thing, but when you write in matrix form, you have to write it this way in quadratic form. All right. Now, if we get the partial derivative of k with respect to q dot here, we will end up with this. So q dot square respects 2 and 1/2 to cancel each other, you end up with mq q dot. And then if you get the time derivative of that, because we're getting the time derivative of this, both of these have elements that are function of time, then we have to use the chain rule. So m q double dot plus m dot q dot. Now, m is your mass matrix. To get the partial derivative, you will get element wise, right? You will get the no partial derivative, time derivative. It's element wise time derivative. So the first expression here gave us this, all right? Now, the second expression is partial of derivative of k, our kinetic energy with respect to q. What was our k? 1/2 q dot transpose mq q dot. Q dots are not function of q because they're q dots, right? The only thing that you can get the partial derivative is m. So I can rewrite that as this. 1/2, that's fixed. Q dot transpose, I can bring the partial derivative inside. So that's the only thing I'm getting partial derivative of. So as you can see, I'm trying to come to a form that's familiar to me. So now these two, if you look at it, you have mq double dot mass matrix times the acceleration from the inertial force plus two expressions that they have their function, they're a coefficient, the coefficient of q dot, q dot, q dot, right? So since m is a function of q itself, so this expression is representing dq q dot, right? And we are familiar with this. This came from the general formula. So I kind of worked from here to reach to my general formula. The rest of it is tau minus gq, which is the potential energy. We're going to work with it. Now, from here, we are going to develop a method to find m directly and to find this v directly from the configuration of a robot, from methods that we have seen before. Tell me what's going to show up. How you can relate the joint variable to your system's motion. Yes. Right? So yeah, Jacobian is going to show up wherever. Mapping your joints, right? So now let's look at a random robot configuration. We are going to work out everything for a random joint, random length, then we can apply. So the explicit method is used, especially when you're writing algorithm, right? It's easier because we're going to find an expression that when you change ijk, it can just give you those elements in your matrix. Now, for a random link I, right, that link could have a linear velocity and or an angular velocity, depending what kind of joint it is and what joint was before it. as when we are generalizing it, we are going to consider both of them, right? And then we're going to say if it's prismatic, doesn't have angular velocity. And then one other thing we're going to consider is the position, the distance of the center of mass of that link to our base frame. So everything is again calculated with respect to our base frame or frame 0. Now, from before, we had this expression for forward kinematic. Sorry, kinetic energy. For kinetic energy, we know we can write 1/2 Q dot transpose M Q dot, right? So I'm going to write that as the left side. I want to see if I can use the system configuration to reach to an expression that's equal, right? So this we know. This equal doesn't mean right away you can see the equality. We're trying to figure out how these two will be equal, all right? Does that make sense? So right away you don't see the equality, but at the end you will see that these two can be equal. We know we can write the linear velocity of a link as the linear Jacobian, the linear part of the Jacobian, right? Times your Q dot. Correct? You're doing the homework. You already submitted? Submitted. Yes. So Jacobian has two parts, linear and angular. We can write the linear velocity to be VCI, Jacobian of linear times Q dot. And also write the same thing for our angular. So omega CI is going to be J omega I Q dot, right? So at any point, so at any link, you could have either of those, right? Now let's write our kinetic energy knowing these two information. So kinetic energy for link I would be 1/2, right? MI of that link, VCI transpose VCI, so it's MV squared. You can't just write V squared, this is a matrix. You can write like that. You can't even bring M inside. This is a fixed number, it doesn't matter. Plus omega I transpose IC, which we saw this before. This is the angular momentum and angular kinetic energy of the angular motion. Omega I transpose IC omega I, right? You know that. From up there, we can replace this with J omega J VI Q dot. Replace this omega I with J omega I Q dot, right? So then we will have IC J omega Q dot. What can we do with these two? Can we write a relationship for these two based on Jacobian? So as you figured, I'm writing things based on Jacobian. Can we find a relationship? So let's see here. So I want to find VCI transpose because that's what I have here. What do I do? Yes. The other side? Yes, you could do that. So you get the transpose of that, you get the transpose of the other one? Yes.
What's the matrix multiplied by matrix on the right and transpose on the left?
What do you mean?
Like you have I B multiplied by omega on the right.
These are vectors, right?
Yeah.
3 by 1, then 1 by 3, 3 by 1. So you can't just multiply 3 by 1 by 3 by 1, right? So that's the significant 3 by 1 times 3 by 3, maybe it's like something in between, and then times the other one. So you can algebraically do it. That's the significance. There is like, so if these were like scalar number, doesn't matter. But when it is, there are matrices and vectors that the dimension matters for doing the actual multiplication. That's the only thing.
Okay.
Yes.
Related to that, so on the second, well, the first line from that bottom set of equation there, we have VC transpose VC IC, but then on the next term, we have omega I transpose. The matrix
Because this
equation.
is a 3x3 matrix. This one just a scalar value. So here I need to have like 3x1, 1x3, and I can do this. That's the reason, because that IC, remember, is 3x3 matrix. That's why you have to, so basically here is configuration to do this major multiplication. If your M was a matrix or a vector, then you had to reorganize, make sure you can do the multiplication. All back to algebra and matrix algebra. All right, so we created VCI transpose based on Jacobian. We have VCI based on Jacobian. Same for the omega. I can just replace them, right? So I'm substituting them and you see what is happening. So this is the summation from I to N to N. Mi q dot, so q dot is not changing with I, it's a fixed constant, it's just a vector of your joint variable. Here, 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 you can factor them out. Maybe this one here, q dot here, and all you have is your Jacobians, right? So we will get, so that was the left side from before. Now the right side became 1/2 q dot transpose a matrix dot times q dot. Now if you compare these two, you'll see that everything looks the same. So this must be your mass matrix, which is, so we can use this formula to create our mass matrix using the Jacobians, right? So what does really mass matrix represent? Is the effect of acceleration of different links on their previous link, right? So if both of them are moving, so the effect of this first one accelerating is going to affect the second one, the second link. If the second link is accelerating, it's not going to affect the first one, or it might affect. So mass matrix is going to evaluate those or explain that. So we can find those relations from our Jacobian, and it comes to mass and inertia, which makes sense if you think about it. So finding Jacobian is important. So if you have a robot, you find the Jacobian, you already know velocity kinematic, you can find the dynamic, right? Because all is because the joint velocity and how joints are related to your end effector. So you have a golden map that can basically solve your problem, right? So this, we will use this equation to find mass matrix. If you compare to the other method, you have to actually find all of the kinematics and potential energy, get all the derivation to get here. Here, all you need to do is Jacobian linear and angular. Now, every time you're rotating, iterating from I to going to N, so when I is 1, it means that you're only looking at the first link, right? So you only have this first terms, everything else you consider 0 because there's no effect from those, your first link. Now, if it's I is 2, I have first one and second one, and everything else is 0 for now. So for any I link, all the joints after that, their effect is 0. It doesn't matter if it is in the linear Jacobian or in angular Jacobian. Then this is basically your populating your Jacobian. So the columns are there, right? It is supposed to be 6x4. It's always 6x4, like 3x4. But you populate it as you move. You're propagating through your links. All right, so that's how you find your mass matrix. Now, once we have our mass matrix, we can use those elements to find the other one, or V vector. So that's the beauty. Everything comes down to Jacobian. You have Jacobian, you find your mass matrix, you use the element of mass matrix to find this. If you remember from up here, we said this is basically, this pink one is our V vector. We called it, right? We said this is going to be V vector. So I'm going to bring that here. M dot Q dot, M dot is element-wise time derivative. So literally, so I'm assuming to make this make more sense, I am using example a 2x2 robot, 2R robot. So M is M11, M12, M21, M22. Okay, so four elements. Now, M dot, Q dot. Q dot is the joint variables. Your M dot is going to be element-wise time derivative. M dot 11, M dot 12, M dot 12, M dot 1. All right. Then the next one, if you remember, we had partial differential of M with respect to Q1. We have M. We are going to use this notation. So we are going to element-wise get the partial differential. So M11, this one, with respect to your first joint, we are going to show it as M111. So here is because of your the element, this is the Q1. So this means partial M11 with respect to Q1. This is partial of M12 with respect to Q1 and such. So we haven't done anything. We're just introducing different notation. So we're going to use this notation. So now we ended up here. Calculating this matrix is not important because it's element wise. Now for M11 with respect to Q1, so if I want to find M dot 11, I'm going to write M111, which is partial of M11 with respect to Q1, Q dot 1, M12 respect to Q2, M112, Q dot 2. So that becomes this element. Actually, this is not a, like you have to find that one first and then this one. All right. So we find all values, like here's 4. We find all 4 of them. Now, I'm rearranging them because I want to put it in a special order. If you expand all of those, write them all, and then expand them, you will end up getting, this is what's important. You're getting this 4x4 matrix multiplied by Q dot 1 squared, Q dot 2 squared. So this is the square of the velocities. And then some matrix multiplied by the product of the velocity. We want to reach to this formation because you remember what these two represent from last class? The quadratic, the square of the velocities versus the product of the velocity. One is centripetal, one is Coriolis, right? So we on purposely we're going that way because it's easier to separate them, and then there is a relationship to just follow to develop these. So you're right. So this one is our centripetal. This is Coriolis forces. Now rearranging, we are gonna get, so we're gonna call that B111, B221. This matrix is called C matrix. This one we're gonna call B matrix. We are using Christoffel symbols, so calling it B112, B111. This is Christoffel symbol. We are going to use that equation up here, that formula, to populate, this is your formula, to populate your C and B matrix. So Bijk is 1/2 Mijk from mass matrix plus Mikj minus Mjki. So follow this formula. If you want to know how it was derived, you just have to do a little bit more research. But for us, having that is enough because then we can populate the two matrices, this matrix and this matrix. We are done almost, right? We already found our M matrix. We found the V, which is Coriolis and centripetal. What is left from the general formula? The gravitational. That should be the easiest one because you have one vector G pointing downward. You have mass of the object, which is fixed, right? The only thing is changing is the distance, right? Basically the height. So we can write our potential energy. G is partial v with respect to Qi. We can write that as mg partial of the distance with respect to our Q, right? Qi. Now, this guy is the linear Jacobian. Partial of the center of the mass of the object with respect to the point variable. This is how you calculated your linear Jacobian. So that's going to be your linear Jacobians times mg, which is fixed. So you can write G as basically this is Jacobian of the first link, the second link, the third link. You've already calculated for your mass matrix. All you have to do is to grab that and multiply by the mass of the link and the gravity, right? So finding Jacobian helped a lot. We found mass matrix, we can directly find this, and we find using mass matrix element to find our Christoffel symbol, which is centripetal and Coriolis forces matrix. Now you can write the general formula to put them all together, right? Yes? Okay, questions?
Go back.
Sure.
Can you write?
Which one? This one? So if there is mistake on subscription, it's just like the too many things to type.
Because when you come back here, you get M1.
For Christoffel symbol, you're gonna follow this. Forget about all of that. That was like how we got here. So you have two things to follow. Christoffel symbols is IJK, because when you have 1 and 2, like they get confusing. This is for Christoffel, and this is for mass matrix, right? So all of everything else was to just explain to you how we got here, how we got where we got. All right. So I'm bad with subscription because like typing in equation and keep changing them out. I'm sorry. I'll try to fix them, but you'll follow this. Now, if we want to solve our previous example using this method, what is our approach? How do we go about it with all the knowledge you just received? And then it's like, yeah, dump of knowledge. So what do you go about? Where do you start? This is the same example. You have I, C1, you already have it, I didn't write it. We are trying to find equation of motion for this. What is your approach using the explicit form? Yes. Now, before mass matrix, what do you need to do? Jacobian, right? So our approach before Jacobian, what is like the little thing you need to do? To identify your Q, what's your, right? Which is here is theta 1 d2. Now find JV and J omegas. Now here you have, like, I'm gonna write all of it. JV1, JV2, J omega 1, J omega 2, right? Because you have two links, so you're gonna have two different Jacobians for each of the links. Then once we have J omega J's, all of our Jacobian, find mass matrix, find M, right? This M includes M11, M12, N21, M22. When you have those, now what do you do? Huh? B. Okay, do you remember the Christoffel symbol? So BIJK, right? Find that. Once you have that, you can form matrix B and matrix C, correct? Once you have that, form V, Q, Q dot. Then what's next? Gravity. Find G, Q, which you already have the Jacobian, should be straightforward. Then what? Cam, what would you do after this step? You just go home. Before you go home, huh?
You just add it all together.
You put it in the general formula. Don't forget, you're trying to find the equation of motion, right? You need a tau somewhere. It might be zero, but you need to put things together. So we put in, oh, why am I doing that? I mean, I'm not in a rush. You guys are in a rush. Put in formula, general formula. General formula. What is general formula? Formula. MQ double dot plus VQQ dot plus GQ is tau. You need to always write that. That is your dynamic. That is your equation of motion. Cool? Yes? Feeling comfortable with this method? No? Absolutely not. That's an honest answer. Well, your class participation is going to be an example video, but I'm going to solve this example pretty quick. Yeah.
The form B from a C.
Huh? Form B and C, then form B, Q, and Q dot. What is B and C?
Yeah.
Here. So after you have the Christoffel, you have B, I, J, K, then you form these two because these are actually the coefficient of Q dot square. So this is square of velocity. Velocities. This is product of velocities. One refers to centripetal force, one refers to Coriolis.
So B and C are the coefficients.
What's that?
So B and C are the coefficients.
They are coefficients, yes.
Okay.
There will be coefficients to these. So this together are your V vector.
Yeah.
You're putting them as packaging as Coriolis and centripetal. All right. I'm gonna start doing that. Class goes until 3:55, right? Okay, cool. How about you get started and solve this? Start from Jacobian. I know my mass matrix is gonna be M11, M12, M21, M22 because Q is theta 1 and D2. The mass matrix is a square, right? I know it's gonna be 2 like this. If you don't know why, go check the lecture before. All right. Send me an email. Great. I like how honest you guys are. He's either sleeping, doing his capstone, or sending emails. And he's gonna get an A. That's the problem. So I wouldn't mind if you still get an A and understand what's going on. All right. So finding Jacobians. I'm gonna write how my M matrix is gonna look like for you, but you go ahead and start Jacobians. Because I know everybody's just waiting for me to do it.
Sure. B 2/3.
Yes. It's like I got this part right. But you have to be careful. I'll get there. So your M is from that summation. I'm gonna include the Jacobians. Transpose JB1 plus J omega 1 transpose IC1 J omega 1 plus M2. It is not M2 to M2. M2 Jacobian V2 transpose Jacobian V1 plus J omega 2 transpose IC2 Jacobian 2. Okay, so I know I need 4 Jacobians. I need these 2 guys plus these 2 guys. Well, more than 4. How many of this that? Oh, these are the transpose, so you don't actually need to do anything. That's just transpose. Okay, 1, 2, 3, 4. I was right. I need 4 of them. Now, to get Jacobian, I'm going to need what? That's the part that you're all waiting for me to do it for you. So look at your system. Wow, that looks very ugly, but. So you have different ways of finding Jacobians, right? Yeah, I'm trying to go fast so you get something out of this. All right. So there are different ways of finding Jacobians, right? If we go back to where I actually told you to do Jacobians, what I said, find the distance from the center of mass of the link to the face frames, right? Get the partial derivative with respect to your Q. We're going to do exactly that. So this is PC1. This is PC2, like center of mass of the first link and center of mass of the second link, right? So PC1 in frame 0 is going to be, this was L1, this was D2. What's going to be? L1 cosine of theta, L1 sine of theta 1, 0. So you don't forget Z here. And then PC2 in frame 0 is going to be what? D2 cosine of theta 1, D2 sine of theta 1, sine of 1, and then 0. Correct? Now I have to get the partial derivative of this. So JV1, so you have to go back here, JV1. If I is 1, so it's JV1 is partial of PC1 with respect to Q1, and then everything else is 0, however many links we will have, because JV1 does not see effect of other links, right? But you need to know how many columns your Jacobian have. So you will allocate 0 to the one that are not there. Yes.
Why don't you add
Because this whole distance is D2. So just use that. So this only rotates with theta 1, right? And the whole distance is called D2. So it's like cosine of theta 1 times D2 and sine of theta 1 times D2. That's why. All right, so JV1, I'm going to write it one time. PC1 with respect to theta 1. Now this is for X, then so basically these 3. So here, this one respect to theta 1, this one respect to theta 1, this one respect to theta 1, right? So this one is L1 sine theta 1, L1 cosine theta 1, and this is 0. We are not done yet though. We have 2 links, right? So we are going to place 0 for the second column because we know the dimension of our Jacobian. We should know. Remember, the columns are the number of the links or the joints you have. The column of the Jacobian are the number of joints you have. Now, JV2 is going to be, now this is interesting. So this is the Jacobian of the first link. So find the center of the gravity, center of mass, only one link, right? And then now if we find JV2, what's that gonna be? So the first one is going to be L1 sine 1, L1 cosine 1, 0. What's the second column? The first column was partial of the position with respect to your first joint variable, theta 1. Now, the second one, the second column is partial of those PC1 with respect to D2, right? So for PC2, oh, D2, what did I write? L1, yeah. That was your question? Yes. So negative D2, D2, and here, so this will be cosine, sine 0. For the first Jacobian, you're getting the partial derivative of first length, center of mass, the distance, with respect to your first joint variable, theta 1. So partial of L1 cosine theta 1 with respect to theta 1 is negative L1 sine of theta 1, and so forth. The second link doesn't have any impact on the first link's Jacobian, 0. Now the second link, you move to the fourth part. We are getting the partial derivative of the center of mass PC2 with respect to first variable. So here with respect to theta 1, then the same with respect to your second variable, P2. So cosine theta 1 becomes just a fixed constant number for that, right? So both of them are 3 by 2, but one does not have the population here because second link does not affect this. Now, I think I'm going to just write J omega and stop there because I don't want to keep you here. Now, how do you write J omega? What do you think J omega going to be? If you go back here, so follow this equation. E naught Z1 for the first one, right? And the second one, you just give 0 because you know the second link does not contribute to the angular Jacobian. So J omega 1 is, the first one is a revolute joint 0, 0, 1, right? The z-axis. This becomes 0, 0 because that's 0. J omega 2 is Z1, Z2. Now, what is J omega 2? I promise you, I will let you leave after you've done this. So the first part is just like that, right? 0, 0, 1. Tell me what is the second one? Still 0, why? The prismatic joint. See, the nature of them are different, right? But it's the same 0, 0, 0. All right, I'll post a complete solution here. Try to complete the class participation. If you didn't do it, submit up to here. Okay, submit up to finding mass matrix.
Is this
No, the class participation question is different, simple. A lot simpler than this.